Hi everyone. Let's start now. So let's solve some gate questions, on decidability. Let's start with our first question. Tell me what is the answer. State the halting problem of Turing machine. This is GATE Computer Science 1988 question. We have to find out, like basically we have to write the statement of halting problem of Turing machine. What is the statement of halting problem? What is that? So the halting problem statement we already know. This is the decision problem. The decision problem statement, if you want to write, the decision problem statement will be like this. So the decision problem, what is that? That is basically, I can say, given a Turing machine, two things are given, correct? Given a Turing machine M and a string W. So two things are given. Okay, given a Turing machine M, comma string W, does M halt on W? Does this Turing machine M halt on W? Halt on W. Okay, so you can notice the question is asking what is the halting problem of Turing machines. So for that we need two inputs. One is Turing machine, another is string, and the question is does M halt on W? Okay, this is the question. This is the decision problem. And what is the language? If you want to write what is the halting problem language, the halting problem of Turing machine language. Okay, so that language will be what? That language will be basically set of encodings of Turing machine comma string, set of Turing machine comma string encoding. This is the encoding of Turing machine comma string. Here you can notice M is a string, sorry, M is a Turing machine, W is a string, W is a string, and we are saying that Turing machine M accepts, halts on W. Turing machine M halts on W. Okay, so this is your language. So like this you can do. Remember, very simple. This is the decision problem statement for halting problem, and this is the language for halting problem. Any decision problem we can convert into a language, and any language we can convert into decision problem. I told you that if there is a decision problem, then you take the set of yes instances. Yes or no? If you have a decision problem, then what you do? You take set of yes instances. You take set of those inputs for which the answer is yes. Then you will get the language. Okay. So like this, this is your decision problem, and this is your language. This is the statement of halting problem, and we already know that this language, this language, if you look at this language, what is this language? This language is recognizable but not decidable. This we have already seen. The proof we have seen, because in the interview they will ask you the proof. Remember, in the GATE exam they will not ask you the proof, but in any interview this is the very famous problem. Remember, and in any interview, if you there is a possibility they will ask you this proof. From theory of computation, if they ask you one question, then this will be that question. Okay, in any interview, if they ask you a single question, if they ask you, then this question they will ask. Okay, halting problem of Turing machine. So this proof we have already seen that this halting problem of Turing machine, this language is RE but not REC. This language is recognizable but not recursive. Okay, so this is recognizable but not decidable. And the proof we have already seen. Do you remember the proof? Do you remember the proof? So anyway, for the proof, what we were doing, so we were assuming this was the proof template. Let me just give you the idea. We have already seen the proof in very detailed manner, but this is the proof basically that this is your language HPTM. First we assume this is decider, step by step. Okay, let me tell you step by step. So what are the steps? So this is your language HPTM, and for that the step one was we assume this is decidable. We assume this language, okay, this is a decidable. If this is decidable, then there is a decider. Okay, so there exists a decider. So there exists a decider D. Okay, for HTM, for HPTM, for this language there exists a decider D. What this means, that there is a decider D. This is the decider D. To this you give any input, Turing machine comma string, it will tell you yes or no. It will definitely halt because this is a decider. So it will definitely halt, and it will tell you yes or no. And it will tell you yes or no. Okay, so this is our assumption. We are assuming that there is a decider. If there is a decider, then what we do? If we have a decider, then what we do? We intentionally create a Turing machine T, correct? Okay, so now we create intentionally. Remember, we create intentionally. Okay, we create intentionally a Turing machine T we create. And what this Turing machine T does, this mechanism I told you, what this Turing machine T will do. So this is your Turing machine T. What it will do? This Turing machine T, it will take input as a Turing machine. So you give input as a Turing machine. Inside it will make two copies. It will make two copies. One copy will be treated as Turing machine. Another copy will be treated as a string. Okay. So inside it will create two copies, and then one copy it will treat, this T will treat one copy as one copy of M as a Turing machine, and this T will treat one copy of M as a string. And then what it will do? It will use this decider. It will use this decider D. It will use this decider D to find out, does M halt on M? To find out, does M halt on M? Now you can notice this will definitely halt. Okay. Now if it says yes, if this says yes, then it means what? If this D is saying yes, if this D is saying yes, it means I am halting on W. Okay. So if this D is saying yes, means M is halting on M. In this situation, what will happen? This T will reject M. Or I can say in this situation, T will loop on M. Okay. And if this Turing machine says no, if this Turing machine says no, it means M is looping on W. It means M is looping on W. In that situation, your Turing machine T that will halt on M. Okay, so here T loop on M and here T halt on M. Very simple. Okay, so this is the intentionally we have created a Turing machine T, and now you can find out the contradiction. Now you can bring the contradiction. Okay, how to bring the contradiction? So here you can notice that this is your Turing machine T you have created. You have created this Turing machine T, and in this Turing machine T, what you do? The input you give as a Turing machine. So now for contradiction, now I want to create contradiction. Remember, I want to create contradiction now. So for contradiction, what we do? Tell me what we do for contradiction. We give Turing machine T. This is your Turing machine T. To this Turing machine T, we give Turing machine T itself. Okay, to this Turing machine T, we give Turing machine T itself. Now what it will do? Internally, it will create two copies, T comma T. One copy will be treated as a Turing machine. Another copy will be treated as a string. Then what it will do? It will give this T comma T to the decider D. To the decider D. This is your decider D. And because we are assuming that D is a decider, so it will definitely halt. Okay, it will definitely halt. Now you can notice that if it says yes, by chance, okay, by chance, if it says yes, then what it means? Then it simply means that T halt on T, correct? T halt on T is string T. So you can notice T halt on T. This means, but if this decider is halting, if the decider is halting and saying yes, if the decider is saying yes, that T is halting on T. Okay, if the decider is saying yes, then what this T will do? Then what this T will do? Then this T loops on T. Then this T loops on this input T, loops on this input T. Now you can notice there is a contradiction. Okay, so because of these two situations, there is a contradiction. So we got a contradiction because of these two. Okay, so because of these two situations, we got a contradiction. This is saying that T is halting on T. This is saying T is halting on T. And this is saying T is looping on T. So we got a contradiction because of this situation. So this proof in detail we have seen. I am just, okay, quickly, this is just a revision of the proof, because this proof is really important. Okay, if you go to any interview, they will definitely ask you this proof. So that is the reason I am just telling you, this is just a revision of this proof. But the detail of the proof Okay, like why we do everything, okay, step by step, everything we have already seen in our lectures. Anyway, so this is your for contradiction. So again, you got a contradiction. If this decider says no, if this decider says no, what this means? Tell me, if the decider says no, then what this means? This means that this T loops on, this T loops on T, correct? Okay, this decider says that T loops on T. In this situation, what I will do? In this situation, I will halt. Immediately, I will halt. Okay, so T halts on T immediately. Now again we got a contradiction. Again, what we got? We got a contradiction. So you can notice this Turing machine, when it sees no, then automatically immediately what it will do? Immediately it will do this. Immediately it will do this. Similarly, when it says yes, then immediately it will do this. Okay, so you got a contradiction in both the situations. So ultimately I can say, what can we say? Tell me, ultimately what can we say? So ultimately we can say that the decider does not exist. Correct or not? Decider D for HPTM, for HPTM does not exist. Okay, so I can say HPTM is undecidable. So we can say HPTM is undecidable. So we have seen that this is undecidable. But how to find out that this is recognizable? Tell me why this is recognizable. What is the reason this is recognizable? What is the reason this is recognizable? So this HPTM, this language is recognizable, is RE. Okay, and what to do? Very simple. Can you basically, this HPTM is RE, because what you can do, you can definitely recognize the members. Yes or no? So we can verify the members. This is your HPTM. If you notice, your HPTM, this language, what is this language? This is set of Turing machine, comma W, where M is a Turing machine, where M is a Turing machine, M halt on W. Turing machine M halt on W. So I can say that this is recognizable. What is the reason this is recognizable? Because we can verify the members. Correct? We can verify the members of HPTM easily. Correct? Yes or no? So we can verify the members of HPTM. So what are the members of HPTM? Tell me, what are the members of HPTM? So the members of HPTM, those are Turing machine M, okay, comma W, M halt on W, M halt on W. So we can definitely verify. And for verification, what we will do? Tell me, for verification, what we will do? Very simple. Just run M on W. Just run M on W. For members, it will definitely halt. When you run M on W, when you run this M on W, for members, it will definitely halt. Just run M on W, then what will happen? For members, it will definitely halt. Correct? Okay, for members, halt. For members of HPTM, I can say it will definitely halt. Because M is halting on W, you are saying. Okay, M is halting on W. So here, what will happen? M will definitely halt on W. M definitely halt on W. Okay, so like this you can do. So what we have done, we have proven that this is RE, we have proven this is undecidable. So we have proven that this is RE but not REC. This language, halting problem of Turing machine, this problem, this language is recognizable but not decidable. Okay, and this is a very famous problem. This is very important problem from GATE exam point of view, from interview point of view, from computer science point of view, and I can say from theory of computation point of view. Okay, so that is the reason we can say that this is the proof. So this is the statement. This is your language halting problem of Turing machine. This is the decision problem. This is the I can say this is the language, and this is the proof. Okay. Now Arnav is asking, sir, member non-member proof, can we give an interview? You can give that. Okay, like it's not a it is basically based on the definition, Arnav. The member non-member proof, that is basically based on the definition of Turing machine. That is not a new thing. That is not a new concept. Okay, if you see the definition of Turing machine, like the Turing machine will halt on members. Turing machine may or may not halt on non-members. Similarly, decider, halting Turing machine, that will halt on members, and that will that will halt on all the strings, member or non-member, but it will accept members, it will reject non-members. So if you notice the definition of Turing machine, if you notice the definition of decider, then based on those definitions, this method is this method, member non-member verification, this method is based on those definitions. Is this clear, Arnav? Is this one clear? So these this member non-member verification method, okay, this is based on those definitions of Turing machine, definitions of decider. But this proof that we have seen, this proof by contradiction that we have seen, this is much better proof. Okay, this proof was given by Alan Turing. This proof, the proof that we have seen, this proof was given by Alan Turing. Okay, and this proof is much better. Let me tell you why. What is the reason? Because this proof covers all the possibilities. Okay, in member non-member proof, let me tell you that you can only apply on Turing machines. Okay, because that is using the definition of Turing machine, that is using the definition of decider. So when you use that method, basically that go method, member non-member verification method, when you use that method, only use that method for Turing machines. Don't use that don't use that method for DFA, NFA, PDA, DPDA. Only use that method for Turing machines, because that method is based on the definition of Turing machine, that is based on the definition of decider. So that method you only use for Turing machines. Don't use that for DFA, NFA, PDA, DPDA, linear bounded automata. Okay, don't do that. Is that clear? Now, let's see this one. This is another GATE exam question. GATE Computer Science 1989 question. So tell me, what is the answer? What will be the answer for this question? Which of the following problems are undecidable? For basically, for which of the following problem there is no algorithm? Undecidable means there is no algorithm. For which of the following problem there is no algorithm? So tell me, what is the answer? Which problems do not have algorithm? So for example, membership problem in context-free languages. This is decidable. This is decidable. Okay. We have CYK algorithm. So membership problem in context-free languages, what you can do, this membership problem of context-free languages. Okay, so this A is basically decidable. And what is the algorithm? What is the algorithm? Whatever is your given CFG, what you will do, whatever is your given CFG, you will convert into CNF. Yes or no? You will convert into Chomsky normal form. Yes, you will convert into Chomsky normal form. You will convert into CNF. So what you will do, very simple, that whatever is your given context-free grammar G, this context-free grammar G, you will convert. There is algorithm. There is algorithm to do this conversion. Okay. How to do this conversion? I told you, first you remove all the unit production, null production, and all the useless symbols. So that is part of this conversion. Agree or not? Yes or no? That is part of this conversion. So what you do, given context-free grammar G, you convert into CNF. Now remember, removal of null production, unit production, and useless symbols, that is part of this conversion. So finally, you will get Chomsky normal form CNF. Okay. Now on this CNF, you can use algorithm number 1 or you can use algorithm number 2. On this CNF, what you can do, this is your algorithm number 1 and this is algorithm number 2. We have already seen that. What is algorithm number 1? On this CNF, you apply the CYK algorithm. On this CNF, on this Chomsky normal form, what you do, you apply CYK algorithm. This CYK algorithm you apply. Of course, two things are given to you. Okay, two things are given to you, context-free grammar and a string W. These two things are given to you. So you convert this to Chomsky normal form and the string W will be as it is. String W will be as it is. Now what you do? Now you apply the CYK algorithm. So now you can apply the CYK algorithm. Remember, this CYK algorithm you can apply on Chomsky normal form. And we have already seen that from any grammar, from any context-free grammar, how can we convert into Chomsky normal form? So for this conversion, there is algorithm. This algorithm we have already seen. So how can we do this conversion? And once you have this CNF, then you can apply the CYK algorithm, and this CYK algorithm, it will take order of n cube time, or I can say it will take order of length of string power 3, this much amount of time. Within this much amount of time, this will tell you membership will be decided. Okay, is that clear? So within this much amount of time, the membership will be decided. So this is your algorithm number 1. What was the algorithm number 2? Once you have CNF, what you can do? Once you have CNF, what you can do? Very simple. We know that if you have string W, you have also string W. So once you have CNF, what you can do? Tell me. We already know that in CNF, for any W, derivation length will be exactly, and that we already know. This fact is the proof we have already seen that given okay, any CNF. So this we already know. What we know? We know that any CNF, any Chomsky normal form, any CFG in CNF, any Chomsky normal form G you have, and string W you have. Okay, any string W you take, then what I can say? Then I can say the derivation length, any string W belonging to LG you take, any string belonging to LG you take, then what I can say? I can say derivation length of W in CNF. What that will be? That will be exactly, tell me what that will be. This derivation length, how much will be the derivation length? The derivation length will be exactly 2 length of W minus 1. Exactly this. Okay, this will be the derivation length. Exactly this will be the derivation length. Exactly this. Not more than this, not less than this. So once you have a Chomsky normal form and any string in the language you take, any string in the language you take, then I can say that the derivation length will be exactly this. Okay, exactly this. So what you can do? You can apply brute force. This is your Chomsky normal form and this is your string. So what you can do? You can brute force. You can apply the brute force here. This brute force algorithm you can apply. And for brute force algorithm, what you can do? You can generate all derivations. You can generate all derivations of length. How much? Of length how much? To W minus 1. Correct? So you can generate all derivations. All derivations you can generate. All the derivations you can generate of length this much. And then you can notice that if any one of them ends, if any one of them ends with W, if any one of them ends with the W, then what you will say? If any one of them ends with the W, then what I can say? Then accept G comma W. Then accept G comma W. Okay, very simple. Then say yes. Then say yes, accept G comma W, means G is halting on W. Okay, I can say. So if any of them ends with W, then I can say that G generates W. Then I can say G generates W. Or I can say, then I can say W belongs to LG. W belongs to LG. Is that clear? If any of them, else no. Else no. Is this clear? Let me know. Okay, very simple. So you have these two algorithms, algorithm 1, algorithm 2. So this problem, the problem first, that is decidable. All the things we have already seen. So this is decidable. And what about the next one? Whether a given context-free grammar is regular. A regularity problem of context-free languages. This is undecidable. I told you in the class we have already seen that for context-free languages, 3 standard problems are decidable. 3 standard problems are decidable for context-free languages. What are those? For CFLs. For CFLs, what are the decidable? Like what are the standard? 3 standard problems are decidable. 3 standard problems that are decidable. Standard decidable problems. Standard decidable problems. Okay, the first is membership. Whether a given context-free grammar will accept a given string or not. So this is your membership. The second is emptiness. The second problem is emptiness. Remember, if emptiness is decidable, then non-emptiness is also decidable. If emptiness is decidable, then non-emptiness is also decidable. And finiteness, if finiteness is decidable, then infiniteness is also decidable. So both these things are decidable. But regularity problem is not decidable for context-free languages. Okay, next, whether a finite automata halts on all inputs. Is it trivial? Whether a finite automata halts on all inputs. Can I say trivially? Yes. Can I say finite automata will always halt? Can I say finite automata will always halt? Can I say? Here finite automata, basically it can be DFA or NFA. We don't know what is this finite automata. This can be DFA or NFA. Can I say NFA will always halt? Given NFA, will it always halt? Given NFA, will it always halt? So this is not trivially decidable, because remember this point we have already seen in the class. Don't forget that point. I told you that given DFA will always halt. Yes or no? DFA, given DFA will always halt. Can a DFA ever go to infinite loop? And the answer here is no. Here the answer is no. DFA can never go to infinite loop. If you have a DFA, M, and you take any string W, if you run this DFA M, on W, then it will definitely halt. Okay, then it will halt. It will halt in theta of n time, in theta of length of W time. Is this clear? Okay, exactly this much amount of time it will take, not more than this, not less than this. So it will definitely halt within this much amount of time. Yes or no? This we have already seen. So within this much amount of time, it will definitely halt. This DFA will definitely halt on any string within this much amount of time, exactly this much amount of time, not less than this, not more than this. Okay, so DFA can never go to infinite loop. So DFA can never go to infinite loop, but NFA can go. But NFA can go to infinite loop. Yes or no? So here, can a NFA go to infinite loop? And the answer is yes, possible. Yes, it can. Because of what? Tell me. NFA can go to infinite loop because of empty moves, null moves. Only because of null moves. Can go to infinite loop. Can go to infinite loop only because of null move. Only due to null moves. Only due to null moves, it can go to infinite loop. This we have already seen. Yes or no? So for example, if you have this type of situation, that NFA can go to infinite loop. If you have this type of situation, consider this. Okay, this type of situation, let's assume. So this is your Q0. Okay, anyway, so if you notice that here the NFA is going to infinite loop. Okay, so can NFA go to infinite loop? The answer is yes, it can go to infinite loop. Like for example, here you can notice your NFA can go to infinite loop. So it can go to infinite loop only due to null moves. If there are no null moves, so basically what I can do, this NFA I can put into different categories. Like there is no null move. Okay, NFA with no null moves. NFA with no null moves. With no null moves. Okay, so this type of NFA can never go to infinite loop. Yes or no? If there is no null move, then this type of NFA can never go to infinite loop. Can never go to infinite loop. Correct? And another NFA is NFA with null moves. Another NFA, that is your NFA with null moves. This may go to infinite loop. Okay, so this is the first point. So DFA can never go to infinite loop. DFA will always halt. And you can notice NFA without null moves, it will always halt. NFA with no null moves, if you notice NFA with no null moves, it will always halt. But this type of NFA which has null moves, it may go to infinite loop. Okay, and this will always happen because of the, and this infinite loop, how it will look like? Tell me. This infinite loop will definitely look like a loop. It will definitely look like a loop. Is this clear? It will definitely look like a loop of empty. Is this clear? Okay. So this infinite loop, remember the infinite loop of NFA, the infinite loop of NFA, that will definitely look like a loop. Okay, that will be a cycle. This infinite loop will be a cycle. Cycle with empty. Is this clear? So this type of loop. So basically, I can call it empty loop. You can call it empty loop. Basically, you can say that this is your empty loop. Okay, this is your empty loop. Now tell me one more thing. So if I give you, so what will be your algorithm? Can you detect it? Tell me, given NFA, it is going to infinite loop. Can you detect? Is there any algorithm which can detect this type of loop? Yes, there is algorithm. Yes, there is algorithm. Cycle detection. You can apply cycle detection algorithm. Okay, some cycle detection algorithm you can apply. Basically, you just need to detect the empty loop. Okay, so remember, you just need to detect the empty loop. So what happens here? Given a finite automata, does it halt on all inputs? Does it halt on inputs? So this problem is decidable. Remember, this problem is decidable. There is algorithm. This problem is decidable, but not trivial. This problem is decidable, but not trivial. Remember, this is trivial for what? If I ask you DFA, now this is trivial, right? Yes or no? If I ask you, given DFA, does it halt on all inputs? Given DFA, does it halt on all inputs? This is trivially decidable. This is trivially decidable. This language is trivial decidable. Just say yes. Just say yes. Okay. So now this is trivially decidable. Now this is trivially decidable. And the same thing you can say if you have NFA with no null moves. The same thing you can say if you have NFA without null moves. If you have NFA without null moves. If you have NFA without null moves, then also you can say decidable, and it also will be trivially decidable. You will just say yes. But if I give you some random finite automata, this can be FA, okay, this finite automata can be DFA or NFA with null moves. Okay, so if I give you some random finite automata, then what we can say? Then will it halt on all inputs? That is decidable, but not trivial. That is decidable. Okay, that is decidable. Now, what your algorithm will be? What your algorithm will be? Your algorithm will be very simple. Check if it is DFA. The given FA, is it DFA? Okay, given F, okay, so given M, is it DFA? Okay, check it, yes or no. If it is DFA, then what you will say? Given M, if M is DFA, given M, if it is DFA, then okay, then just say yes. Then just say yes. Similarly, given M, if no null moves, then also say yes. Okay, and given M, else what you do? Else find null cycle. Okay, else find null cycle, empty cycle in an, okay, in given FA. Is this clear? Okay, so else find null cycle in given FA between start state and final state, between Q0, between Q0 and some final state, between Q0 and some final state. Tell me, did you get it? Is this clear? Anyone has any doubt? Is this explanation crystal clear? Tell me, did you understand what is happening here? Given a finite automata, will it halt on all the inputs? Will it halt on all the inputs? This problem is decidable very easily. This is decidable. All you have to find is just find the null cycle, empty cycle. Just find the null cycle. This null cycle you have to find. This type of null cycle you have to find. Okay. So remember, when I say null cycle, what I want to say? When I say null cycle, or I can say empty cycle, then this type of cycle I am talking about. I am talking about this type of cycle. Okay, I am talking about this type of cycle, like it can go, it can go, it can go, it can go. Okay, ultimately it is coming back and empty. So this type of cycle we are talking about. Okay, so this is the explanation. So this problem is decidable. Let me give you one note. Let me give you one note. The halting problem of Turing machine we know, yes or no? The halting problem of Turing machine we know is undecidable, correct? That we know. Halting problem of Turing machine is undecidable, right? Halting problem of Turing machines. Halting problem of Turing machines is undecidable. This we already know. But halting problem of these machines, the halting problem of DFA, the halting problem of NFA, the halting problem of DPDA, the halting problem of PDA. Okay, these machines, the halting problem of these machines is decidable. Okay, so they may or may not halt. For example, PDA, this DPDA or PDA, because of null moves, they may or may not halt, but we can always decide it. So halting problem is not a problem. This we have already seen. Yes or no? I told you that infinite loop is not a problem. Infinite loop is not a big issue. Is not an issue. Is not an issue. Okay, is not a big issue. I can say is not a big issue. In finite automata and PDA. Is this clear? DPDA. So infinite loop is not a big issue. Okay, infinite loop is not a big issue. This infinite loop, it can be detected. Can be detected using algorithm. You can detect it using algorithm. Can be detected. And this loop, this infinite loop, it will always look like this. And this will always be an empty loop. This will always be empty moves loop. For these machines, for them. Tell me, is this point clear? Let me know. So for these machines, this infinite loop is never a problem. So this is decidable. The halting problem is decidable for DFA, NFA, DPDA, PDA. The halting problem is decidable. Okay, so the halting problem is not a problem. The halting problem is not a big issue for DFA, NFA, DPDA, PDA. Like for example, I told you these may or may not go to infinite loop. NFA, DPDA, PDA. These may go to infinite loop. Okay, but you can always detect it. These infinite loops can always be detected. There is algorithm to detect these loops, and the loops, the infinite loops in these machines, they will always be empty move loop. Okay, null moves, null move loop, null loop. Okay, so this is your question. I just wanted to tell you here, this is a very easy question if you notice. So this problem is decidable, but this is not trivially decidable. Did you understand? Please tell me. So this problem is decidable. Whether a finite automata halts on all the inputs this problem is decidable. Okay. But this is not trivially decidable. Many students, what they think, oh, finite automata can never go to loop. Finite automata can never go to infinite loop. PDA can never go to infinite loop. DPDA can never go to infinite loop. But that is not true. PDA, DPDA, NFA, these can go to infinite loop. They may go, they may or may not. Okay, they may go to infinite loop, but we can decide it. We can detect it. There is algorithm to detect infinite loop. Okay, so infinite loop is not a big issue for these machines. So whether a given finite automata halt on all inputs, this problem is decidable. There is algorithm to decide it. Okay, tell me the next one. Membership problem for type 0 languages. That means RE languages. Type 0 languages means RE languages. Membership problem for RE languages, that is undecidable. Do you remember the proof? The proof we have seen that this is undecidable. Do you remember the proof? Very simple proof we have seen, proof by contradiction also, and membership, non-membership proof. So this option D proof we have already seen. Correct? Okay. So now let's move on. So here, remember this D, problem number D. What was that? That was your membership problem of RE languages. That is membership problem of RE languages. Problem of RE languages. What that means? That simply means that this is your ATM, correct? What we call it? We call it ATM, acceptance of Turing machines. Acceptance problem of Turing machines. So here you have a Turing machine M, W, such that Turing machine M accepts W. This is the membership problem. Can you apply Rice theorem here? Can you apply Rice theorem here? Can you apply Rice theorem here? Two things are given to you. Can you apply Rice theorem? Rice theorem cannot be applied. How many times will I tell you? Rice theorem cannot be applied. Is this clear? Rice theorem cannot directly be applied. Of course, we can do some conversion. Cannot directly applied. You cannot directly apply it. In the next lecture, in the reduction chapter, we will see. But do you remember this? I told you everything. When the Rice theorem is applicable, when the Rice theorem is not applicable. This we have already seen. I told you in this type of situation, Rice theorem is not applicable. Rice theorem has a fixed format. Rice theorem has a fixed template. Rice theorem has a fixed template. There is a fixed template for this. Okay. So remember, Rice theorem cannot be applied in this type of situations where you have Turing machine, W, or 2 Turing machine, 3 Turing machine, DFA, NFA, okay, PDA, context free grammar. In these type of situations, Rice theorem is not applicable. Rice theorem has a fixed template. Rice theorem says that give me one Turing machine. Don't give me these type of two things. Don't give me 2 or 3 things. Don't give me CFG. Don't give me PDA. Don't give me DFA. Rice theorem says that give me single Turing machine and ask me a question about its language. Yes or no? Clear? So what Rice theorem says? This we have already seen. What Rice theorem says? Rice theorem, what it says? It simply says that give a Turing machine, give a single Turing machine. That's it. Give a Turing machine M and ask a question about its language. And ask a question about LM. This is your Turing, this is your Rice theorem. So we have already seen Rice theorem is not applicable, but we have already seen the proof. So Rice theorem is not applicable, but this proof, this was the first proof we have seen, correct? Do you remember? ATM, Turing machine M accepts W. So we have seen two proof we have seen. We have seen proof number 1, okay, and we have seen proof number 2. This proof, this by contradiction proof we have already seen. Okay, and this is member non-member verification. Okay, so both of them we have already seen. Okay, so membership problem of RE languages, that is undecidable, and two proof we have seen. Proof number one, proof number two, both of them we have seen. Okay, so let's move on now. So this problem is undecidable. So for this last question, what is the answer? So for this question, the question is asking what are undecidable. The question is asking what are undecidable. So I can say regularity problem of context-free languages, that is undecidable, and membership problem, okay, that is undecidable. Mavit is asking, sir, for regularity problem, can we say recognizable? No. Mavit, actually, problems related to context-free languages, these are much complicated than problems related to Turing machines. Okay, Mavit. So don't worry about the problems related to context-free languages. From CFLs, they will ask you only the standard questions. Let me tell you. Is that clear? From CFLs, they will only ask you standard questions. So this I've already told you that from CFL, okay, basically the decidability decision problems, okay, the decision problems of CFLs, the decision problems of CFLs, they are much complicated than, they are much complicated. Okay, you will see this in your MTech. Do your MTech from IIT, ISC, okay, top colleges, okay, then take the automata theory course, TOC course. Then you will see this, that decision problems of CFLs, these are much complicated to prove. These are much complicated to prove than decision problems of Turing machines. Then decision problems of Turing machines of RE languages. In the next lecture, actually, we will prove it, all of them. Yes or no? In the next lecture, we will prove all of them. We will prove. But here, how many I proved? Do you remember? Decision problems of CFLs. How many I proved? 3 of them I proved. Yes or no? Decision problems of CFLs. 3 of them we have proved. So this is what I'm saying. Decision problems of CFLs. These are much complicated to prove than decision problems of RE languages. So this will happen. Remember, in your GATE exam, they will only ask you standard questions from this area. Okay, in GATE exam, they will only ask you standard questions. In GATE, only standard questions will come from this. From this, anything can come. Yes or no? From this, anything can come. Anything can come. Because there is Rice theorem here. So you have Rice theorem, you have member, non-member verification method. There are many methods here. So from this area, any question can come. A lot of questions we have done. Yes or no? From this area, decision problems of RE languages. A lot of questions we have already done. So from this area, anything can come. But from this area, decision problems of CFLs, from this area in GATE exam, only standard questions can come. Okay, let's move on now. Now let's see this one. What is the answer here? Tell me. Which of the following statement is false? The question is asking false statement. And this is a GATE Computer Science 1996 question. The halting problem of Turing machine is undecidable. We have already seen that this is undecidable. Okay, so this is actually true. This statement is actually true. The question is asking false statement, but this statement is actually true. The halting problem of Turing machines is undecidable. The proof we have seen. Next, determining whether a context-free grammar is ambiguous. Determining whether a context-free grammar is ambiguous, that is undecidable. This is also true. Ambiguity of context-free grammars, that is undecidable. Okay. Next, given two arbitrary CFG G1, G2, it is undecidable whether they are their language is equal. Their language is equal. Basically, equivalence problem of context-free languages. This is also true. This is undecidable, correct? So this is also true statement. Because this is equivalence problem. Do you remember? This is equivalence problem of CFLs. So I can say that this is your equivalence problem of CFLs. This is the equivalence problem of CFLs. Okay, next. What about next? Given two regular grammars, it is undecidable. This is equivalence problem of regular languages. This is equivalence problem of regular languages and no. So here I can say this is the false statement. This is the false statement because this equivalence problem of regular languages, that is decidable. And what is the algorithm? For this, what algorithm you will use? You can create, if you want to see they are equal, then you can create a product automata. Yes or no? You can create a product automata for which operation? You can create product automata for exclusive OR, for this operation, for XOR operation. So you can create product automata for XOR operation. Then you can check emptiness. Then you can check emptiness. Okay, so this is a false. Now let's see the next question. Tell me about this one. This is GATE 2000 question. Consider the following decision problems. Two decision problems are given to you. Whether a given finite state machine accept a given string. This is the membership problem, and this is a very much decidable. This is very much decidable. Okay, next. So does a given context-free grammar generate infinite number of, this is infiniteness problem. This is also decidable. This is also decidable because this problem P2, this is infiniteness problem of CFLs. This is infiniteness problem of CFLs, and this is also decidable. What is the algorithm for the first one? For P1, what is the algorithm? For P1, what is the algorithm? For P1, what will be the algorithm for P1? For P1, given finite automata, what you do? Given finite automata, okay, you convert into DFA. Given finite automata, you convert into DFA. Given finite automata, you convert into DFA. So whatever finite automata is given to you and a string is also given to you, then very simple. What you do? You convert into DFA. Okay, and then now it is very simple. Now it is very simple. Now just run. Now what you do? Now you run this DFA on W. Okay, how much time it will take? It will take theta of length of W, this much amount of time. So this is your algorithm for P1. Finite, yes, finite state machine means finite automata basically, because see, this is talking about given string is accepted or not. Mavit, here the word finite state machine, this is actually here, this is actually finite automata. Yes or no? We have already seen that finite state machine is a big thing. This we have already seen in the digital logic. I told you that finite state machine, okay, for example, finite automata is a finite state machine. Your Mille-Murray machine, these are finite state machine. Mille-Murray machine. Your sequential circuit, or I can say synchronous sequential circuit. So your sequential circuit, that is also finite state machine. There are many more. Yes or no? Anything which have finite number of states, that is a finite state machine. So this we have already seen what is a finite state machine. But you can notice in the question, in this question P1, the question is saying, does a given finite state machine accept a string? So which type of finite state machine he is talking about? Tell me, Mavit. Read the question and tell me which type of finite state machine he is talking about. He is talking about DFA, NFA, finite automata. Okay, he is talking about finite automata. So from the question you can understand which finite state machine he is talking about. The question is talking about. So this P1 is decidable. The algorithm is here. whatever finite automata you have, convert into DFA. If you have DFA, very good. If you have NFA, convert into DFA, and then you run the DFA very easily. Okay, next. Here, what about P2? This is your infiniteness problem of CFLs. So what is the algorithm for P2? Infiniteness problem of CFLs. So for this algorithm, we have already seen cycle detection. Basically, what you will do, given context-free grammar, any given context-free grammar, what you will do, first you will convert. Okay, first you will remove all these things. So, okay, so you will remove, remember, you will remove null production. You will remove null production. What you will do, you will remove unit production. And you will remove useless symbols. Okay, you will remove useless symbols. So this is what you will do. Also, you will convert. Also, you will convert into CNF. Chomsky normal form. So finally, you got a CNF. So finally, you got a CNF. The CNF you got. Now for this CNF, what you can do? From the CNF, you will create the reachability graph. From the CNF, you will create the reachability graph. This reachability graph you will create. This reachability graph, let me call it reachability graph P. This reachability graph P you will create. And then you can notice very simple that I can say the language is infinite. I can say LG is infinite if and only if there is cycle in P. If and only if there is cycle in P. If and only if there is cycle in this reachability graph. So this reachability graph you will create. Once you have this CNF, once you have this Chomsky normal form, okay, once you have this, then what you will do? For example, there will be productions like this. A goes to B, C. This type of productions will be there. A goes to A. This type of productions will be there. So what you will do? You will create the reachability graph. This reachability graph you will create, and here this is what you will do. That A is going to B. Okay, this C is reachable from like this. This type of reachability graph you will create from this based on this, and finally you will find the cycle. Finally, you will find the cycle. So if there is cycle, the language is infinite if and only if there is cycle in this reachability graph. So this is your algorithm. So very simple algorithm we have already seen. You can read this. Okay, you can read this very easily. So this is the idea. So both these problems are decidable. So the question is asking which of the following statements are true? Both P1, P2 are decidable. Yes. Answer is option A. What about this question? Tell me what is the answer. Tell me what is the answer for this question. Which of the following problems are undecidable? This is GATE Computer Science 2007 question. Which of the following problems are undecidable? Membership problem. The question is asking for undecidable. Membership problem of CFG, that is decidable. Membership problem of CFG, that is decidable. Many times we have seen the algorithm. Ambiguity problem of CFG, that is undecidable. That is undecidable. Ambiguity problem. Finiteness problem of finite automata. Finiteness problem of finite automata, that is decidable. That is decidable. And what about equivalence problem of finite automata? Equivalence problem of finite automata, that is also decidable. Okay, so all these algorithms we have already seen anyway. So the equivalence problem is already decidable. So the question is asking for undecidable. So the answer will be option B. Answer will be option B. So all these algorithms we already know. Do you know the algorithm for finiteness of finite automata? How to check? How to check what is the algorithm for finiteness problem of finite automata? What is the algorithm for this? Do you remember? Again, cycle. Okay, what we do, we convert into DFA. We convert into DFA. So whatever finite automata is given to you, we convert into DFA. In this DFA, what we do, From initial state to final state, we see there is a loop or not. We see there is a loop or not. From initial state to final state, we see there is a loop or not. If there is a loop, then language will be infinite. If there is no loop, then language will be finite. So we check this loop is there or not. So this is the algorithm. If this loop is present, then language will be infinite. And if this loop is not present, then language will be finite. Now let's see the next question. Okay, so anyway, this we already know that these two problems are undecidable. What is this problem? Tell me what is this problem? Context-free grammar generates all inputs. What is this problem? This is your universality problem. This is your universality problem for CFLs. For CFLs. Sigma star problem for CFLs. So anyway, these things are undecidable. These two things are undecidable. Okay, let's move on. Now, tell me about this one. What is the answer for this question? This is GATE Computer Science 2008 question. Which of the following problems are decidable? The question is asking for decidable. Whether the intersection of two regular languages is infinite. This is decidable, no problem. Okay, what you do? First, you find the product automata. First, you create the intersection of two regular languages. Yes or no? First, you create the intersection of two regular languages. First, you find the product automata, and then you find is there any loop. Then you find is there any loop from initial state to final state. Is there any loop? Next, whether a given context-free grammar language is regular. This is undecidable. This is regularity problem of CFLs. Regularity problem of CFLs. This is undecidable. Next, whether two PDA accept the same language. This is equivalence problem of CFLs. This is equivalence problem of CFLs. Equivalence problem of CFLs. Next, whether a given grammar is context-free. Whether a given grammar is context-free. Whether a given grammar is context-free. This is decidable. The question is not about the language. The question is not about the language. The question is about the grammar. Is the given grammar context-free? Okay, tell me. If I say given grammar, which type of grammar I am talking about? Tell me. This is my first question. When I say given grammar, then without mentioning what type of grammar, then what I'm saying here, then what grammar I'm talking about? If I say given grammar without mentioning which type of grammar, if I say given grammar without mentioning which type of grammar, then which grammar I am talking about? Then I am talking about type 0. Yes or no? So if I say given grammar, then basically I am talking about type 0, because type 3 is also type 0. Yes or no? A regular grammar is also type 0. Context-free grammar is also type 0. Your type 1 grammar is also type 0. So when I say that given grammar, so here I am talking about what? So here, this is your type 0 grammar I am talking about. Yes or no? Most general grammar. Most general grammar, because this is the most general grammar. This is the most general form of the grammar. This is the most general form of the grammar, this type 0 grammar. So when I say given grammar, which type of grammar I am talking about? Given grammar. It means I am talking about the most general form of the grammar. And what is the most general form of the grammar? That is type 0 grammar. What is the another name for type 0 grammar? This type 0 grammar, what is the another name? The another name is phrase structured grammar. Phrase structured grammar. And what is another name? The another name is unrestricted grammar. Unrestricted grammar. Or you can call it RE grammar. or you can call it RE grammar. Grammar for RE languages. Okay, so these are different names for type 0 grammar. So when I say given grammar, I am talking about type 0 grammar. Okay, then we are talking about, okay, very simple. Now tell me the difference between these two questions. If I ask you, consider these two questions. Let me call P1 and let me call P2. The first question is, given grammar G is LG CFL, is LG context free. Is LG context free? And the second statement is, given grammar is G context free. Which of these problems is decidable? Which of these problems is undecidable? Tell me. Two statements I am giving you. Which of these problems is decidable? Find decidable or not. Find decidable or not. So tell me, what is this problem P1? If you notice this problem P1, here you can apply the Rice theorem. Yes or no? Here you can apply the Rice theorem. Here you can apply the Rice theorem, correct? When I say given grammar, what I am talking about? What is this? When I say given grammar, what it means? Given grammar, what it means? It means this P1. What is this P1? This P1 is basically given a type 0 grammar. Given a type 0 grammar G is LGCFL. This is the template for Rice theorem. Do you remember? Yes or no? This is the template for Rice theorem. This is your template for Rice theorem. This is basically this type 0 grammar you can convert into Turing machine. This you can convert into Turing machine. This you can convert into Turing machine. You can convert into Turing machine. Okay, so basically this is like G comma only given type 0 grammar. This is the point. Here G is a type 0 grammar. And LG is CFL. And LG is CFL. So here this is the property. This is the property, correct? Here this is your property. So remember this P1. Here on this P1 you can apply Rice theorem. Yes or no? On this P1 we can apply Rice theorem. This is the Rice theorem template. This is the template for Rice theorem. I already told you in the last class what are the templates of Rice theorem. Do you remember? Please tell me anyone has any doubt in this. Apply Rice theorem, because this is the template for Rice theorem, because the given type 0 grammar, okay, given type 0 grammar is the language CFL. So basically it is like given Turing machine is the language CFL. This is Rice theorem. This is non-monotonic property, non-monotonic, non-trivial property. So what I can say about this P1? What can I say about this P1? Tell me. So this P1, if you notice this P1, this is like Turing machine M, and LM is CFL, and the language LM is CFL. So this is the CFL. This is the property. This is the property P, and this property P for RE languages. What can I say about this? For RE languages, what can I say about this property? For RE languages, this is non-trivial. This is non-trivial and non-monotonic. So what can I say about this P1? This P1 is RE but not REC. Sorry, this P1, because of non-monotonic, this is actually not RE. So this P1 is actually not even recognizable. Okay, very simple. Now this second question, what the second question is saying. So this is not recognizable. So this is undecidable. We already know this is undecidable and unrecognizable. What about the second one? What about P2? P2 is saying given grammar, is it context free? Given grammar, is grammar context free? Is grammar context free? Okay, this is decidable. Is grammar context free? This is decidable. What you will do? This is decidable. All you have to do, just check the syntax of the grammar. Yes or no? What you need to do, just check syntax of the grammar. Just check production rules of the grammar. Production rules of the grammar. Yes or no? Just check production rules of the grammar. You only have to check the production rules of the grammar. So this problem is decidable, and you can see that the production rule must be like this. Just check the production rules. You don't have to do anything. Okay, just check the production rules. Just look at the production rules. The production rules must be like this. Variable going to anything. Variable going to anything. So just check the production rules. If the production rules are like this, one single variable going to anything, then that is context free grammar. So this is decidable. All you have to do is just check all the production rules. Just check the production rules of the grammar. Okay, is this clear? So please understand the difference between P1 and P2. Is the difference clear? What is P1 and P2? In the P1, I am saying is the language context free, is the language CFL, and in P2 I am saying is the grammar context free, is the grammar context free. So is the grammar context free? Just check the syntax of the grammar. But this is complicated. Is the language context free? So finally, what will be your answer for this question? So for this question, the question is asking decidable. So what are decidable? That is 1,4. 1,4 is decidable. This is your GATE 2008 question. So 1,4 are decidable. Now let's move on. Let's see this question. Tell me what is the answer. Which of the following problems is or are undecidable? Given a context-free grammar, this is emptiness problem. This is emptiness problem of CFLs. Emptiness of CFLs. This is decidable. What was your algorithm? Is the start variable? Is the start variable useless? Yes or no? Is the start variable useless? This is decidable. Check start variable is useless. Check if start variable is useless. Is useless. Check if the start variable is useless, or I can say non-generating. Check if the start variable is non-generating. Very good. Check if the start variable is non-generating. Check if the start variable is non-generating. Or I can say useless. Anyway, both are correct. There is no problem. Both are correct. Next, what about the second one? What about the second one? This is universality problem. This is undecidable. Universality problem of CFL. This is undecidable. Next, M is a Turing machine. Regularity problem of RE languages. This is undecidable. Regularity problem of, what is the reason? Here you can apply for this third one, you can apply the Rice theorem. This is the Rice theorem material. This is the Rice theorem material. This is the Rice theorem question. Rice theorem material. This third one is actually unrecognizable. This third is actually unrecognizable. This third is actually not RE. Okay, this is your Rice theorem material. Next, what about this next one? A DFA, NFA. This is equivalence problem of regular languages. This is your equivalence problem of regular languages. This is decidable. What your algorithm will be? What your algorithm will be? This is decidable. This is equivalence problem of regular languages. This is equivalence problem of so what you will do? Very good, very good. First, you will convert this NFA. This NFA you will convert to DFA. Then you will create product automata, and then you will create product automata for XOR operation, and then you will check emptiness. Yes or no? In the fourth one, in this fourth one, given DFA, one DFA is given to you, one NFA is given to you, and the question is asking is L of D is equal to L of M. Okay, so for this, what your algorithm will be? Algorithm is very simple. This DFA as it is, this DFA as it is, this you convert, this you NFA, this you convert into DFA. Okay, so this you convert into DFA. Very simple. So first, this NFA you convert into DFA, and now what you do? Now from these two you can create product automata. You can create product automata for exclusive OR operation. For exclusive OR operation. For this operation, you can create product automata, and then you check emptiness. And then you check emptiness. Then you check emptiness. Tell me here, if empty, if yes, if empty, then you check emptiness. If empty, then you accept, then they are equal, okay. If empty, then LD is equal to LM, okay. Else no, else they are not equal. Okay, so this is decidable, and this is your algorithm. This is your GATE 2013 question. Very simple, right? So the question is asking which is undecidable. So the answer will be what? Answer will be second and third. So answer will be option D. Okay, tell me about this one. Okay, so these GATE questions we have done. Please tell me, are you having crystal clear understanding of everything? Are you having crystal clear understanding of everything? See, all these questions that we have done, all these questions we have done, every question that we have done the question with, I can say, complete analysis, with the reasoning, with the logic, with the algorithm. Okay, and all the, I can say, all the aspects of the question, each and everything we have focused, each and every word, each and every aspect of the question. Okay, so this is what we have done. So I hope you understood everything here. Is this clear? All these questions. See, let me tell you, it is very, you can see, it happens. It happens that students, what they do, they solve these questions from the table. Many students, they solve the questions using the table. There is a table. Using that table, they will try to solve the questions, but they don't understand the questions. They don't understand what is the logic, what is the reasoning, what is the concept. Okay, and that is not good, because in the GATE exam they can ask you anything. In the GATE exam, they will know, it is not necessary that they will ask you from the table. They can ask you anything. So if your logic is good, if your logic is perfect, okay, if your understanding is good, then you can solve any question, any variation. Okay, so these are some GATE questions that we have done. Please tell me the answer for this question. Tell me the answer for this one. So actually this we have done in the last class, correct? This we have already done in the last class. Okay, so this we have done in the last class. This is Rice theorem material. All these are Rice theorem materials. All of them, these are basically Rice theorem materials. So this question we have already done in the last class. You can check it out. Okay, anyway, let me give you the answer, because we have already seen this infinity test of this first one. What can I say about first one? This is not RE. All these questions are based on Rice theorem. All these questions, these are basically the Rice theorem questions, all of them. These are Rice theorem material. So this is not RE. What about the second one? This is also not RE. What about the third one? This is also not RE. What about this one? This is also not RE. What about this one? This is decidable. This is decidable. This is trivial. This is trivially no. Just okay, obviously no. So this is actually trivial. Always no. Printf no. Very good. Printf no. And what about this one? What about this one? This is not RE. Non-monotonic property. This is not RE. Okay, let's move on. Let's see this question. What is the answer here? Tell me. Again, this is a Turing machine. Single Turing machine accepts at least 10 different strings. Is this a language property? Is this Rice theorem material? Is this Rice theorem material? A Turing machine T. Here M is Turing machine. Here M is Turing machine. And the question is that LM cardinality is greater than equal to 10. LM cardinality is greater than equal to 10. Yes or no? The question is about the language. Nikhil, the question is about the language. The question is about the language of M. The question is about the language of M. The question is this: LM contains at least 10 different strings. This is the question. Yes or no? LM cardinality is greater than equal to 10. Language cardinality is greater than equal to 10. So this is your Rice theorem material. Yes or no? Just apply the Rice theorem. So if you apply the Rice theorem, then what will happen? This we have seen in the last class. This is RE but not REC. Okay, because you can verify the members, right? You can verify the members, correct? This is RE. Why? What is the reason this is RE? Because you can verify the members using what? Can verify members of L using dovetailing. Using dovetailing. Okay, and you can notice this property. This is non-trivial property. This is non-trivial property. So because this is non-trivial property, so this is undecidable. Because this is non-trivial property. Now let's see this one. This is the statement of Rice theorem, correct? Yes or no? This is actually the statement of the Rice theorem. The Rice theorem statement. This is just another way of writing the same statement. Another way of writing the same statement. This is the another way of writing the same statement. This is your Rice theorem statement. Basically, this is saying that if it is non-trivial property, then it will be undecidable. Okay, language of Turing machine. Now let's move on. Anyway, this is just another way of writing the same statement. Okay, tell me about this one. The question is blur, but anyway, you can read it and tell me the answer. The question is taking from a standard resource, and the question was blur. So I took it. Anyway, so you can read the question. It is not very hard. So the first question is membership. All these questions are membership problem. Yes or no? All of them are membership problems. All of them. These are membership problems. All of them are membership problems of various models. Of various models. So for example, here you can notice DFA comma string. DFA comma string. Okay, so this is decidable. This is decidable. NFA comma string. This is also decidable. W belongs to L of N. All these are membership problems. Remember, all of them are membership problem of various models. PDA, this is also decidable. Next, Turing machine. This is undecidable. Membership problem of Turing machines. Membership problem of Turing machine, that is undecidable. Okay. And I think this is this. I think this is like this. I think this is like this. Okay. I think it is like this. So anyway, this is decidable. What about this one? So anyway, this is decidable, right? For DFA, this membership is also a problem. This membership. So, okay, membership or non-membership problems. These are basically what I can say. Either they are membership problem or non-membership problem. Okay, they are basically membership or non-membership problem. Yes or no? So here, so this fourth one, tell me this fourth one. Can I say this is RE? We have already seen this is acceptance problem. So this is RE but not REC. This is RE but not REC. What about the fifth one? What about the fifth one? Can you verify the members? Can you verify the members? Can you verify the members? So this is not RE. Can you apply Rice theorem? On the fifth one, can you apply the Rice theorem? Rice theorem you cannot apply. Then what you will do? No, this is not LD. This is not diagonalization problem. Mavit, the diagonalization problem was different. See, the fifth problem is this L5. What is this L5? This is Turing machine comma W such that Turing machine M does not accept W. Does not accept W. This is not LD. What was LD? Can anyone tell me what was LD? LD was single Turing machine. LD was like this. Single Turing machine does not accept its own encoding. This was LD. Does not accept its own encoding. This was self non-accepting language. Or you can call it diagonalization language. Okay, is this clear? Self non-accepting language, or I can say diagonalization language. And we have already seen, we have proven it. The proof we have seen, this is not RE. Okay, next. What about this one? L5. M comma W. Turing machine M does not accept W. You cannot apply the Rice theorem, correct? So for this question, okay, you cannot apply the Rice theorem. You cannot apply the Rice theorem. So when Rice theorem is not applicable, what is the best method? The best method is our Go method, or I can say membership non-membership verification method. Membership non-membership verification method. But that method is only useful for Turing machines. Okay, remember this point. Don't make this mistake. This what we call Go method. Basically, this Go method, or I can say this is basically member non-member verification method. So this is, remember, this method you need to apply only for Turing machines. Apply only for Turing machine related questions. Don't apply for DFA, NFA, all these things. Is this clear? Don't apply for DFAs, basically NFAs, context-free grammars, PDAs, etc. I hope this point is clear. So anyway, you can apply this method here. So tell me what will be the answer. So Turing machine does not accept W. Can you verify members? Can we verify members of L5? Can we verify members of L5? Just tell me, can we verify members of L5? What are the members of L5? Members of L5 are Turing machine M, W such that M does not accept W. Such that M does not accept W. Okay, such that M does not accept W. So here you can definitely see that. Can you verify members? So can you verify members? The answer is no. Can you verify members? The answer is no, because if you run this Turing machine M on W, then if you run this Turing machine M on W, then because it does not accept W, may not halt. It may never halt. When you do this, then it may never halt. So I can say, can you verify members? The answer is no. And so because of that, what I can say about L5? So because of that, I can say this is not RE. You don't even have to check for non-members. Actually, you can verify the non-members. So what it tells you? Actually, you can verify the non-members. What it tells you? It tells you the complement is recognizable. Yes or no? You can verify the non-members. What it tells you? It tells you the complement of L5 is recognizable. Yes or no? We can verify non-members, right? Correct. So we can verify non-members. So for L5, I can say for L5, we can verify non-members. We can verify non-members. What it tells you? Hence I can say L5 complement is recognizable. Okay, so this is your question. So this is not RE. Okay, let's move on. Tell me about this one. What about this one? This is Rice theorem material or not? Is this Rice theorem material or not? So this is Rice theorem material, correct? So here, tell me what will be the answer? The language cardinality, L2, set of Turing machines, and the language cardinality, the cardinality of the language is equal to 2. M is accepting exactly 2 strings. Okay, so this property, if you notice, this is a property. This is the property P, and this is non-trivial. You know, this property P is non-trivial, and this is non-monotonic. And this is non-monotonic for RE languages, for RE set. So because of non-monotonic, non-trivial, because of this, I can say that this L2 is not RE. Can dovetailing help you? Tell me here. Can dovetailing help you? No. What is the reason? What is the reason? Because remember, you have to make sure. See, once you accept 2 strings, is that enough? Once you accept 2 strings, is that enough? No, that is not enough, right? Once you accept 2 strings, that is not enough. That is not enough. Because once you accept 2 strings, then you have to make sure that all other strings are rejected. Okay, you have to make sure that all the remaining strings must be rejected. So I can say that this dovetailing cannot help you. And what about this language? Quickly tell me, what is the answer for this one? The language is 0 star 1 star. Can I say this is regularity problem? Can I say this is regularity problem? Can I say this is regularity problem? No, this is not regularity problem, remember. Because regularity problem means the language is regular, any regular. This is not regularity problem, because when I say regularity problem, it means the language is regular, any regular. Okay, is this clear? Are you getting my point? This problem is not regularity problem, because if I say regularity problem of Turing machine, then that means the language must be regular. But that regular can be anything. But here the language must be this. So tell me, what about the answer here? This property, P, this is non-trivial. What about monotonic or non-monotonic? Monotonic or non-monotonic? This is non-monotonic. This is a non-monotonic. Why this is non-monotonic? This is the regularity problem. See, can you understand the difference between these two? Two problems I am giving you, and can you understand the difference between these two? One problem is this: set of Turing machine where M is a Turing machine and LM is regular. And another problem I am giving you where M is a Turing machine and LM is 5. LM is empty. Which is regularity problem? Is this clear? Ekta, please tell me. So this is regularity problem. So this is a regularity problem. Is this clear now? This is the regularity problem of Turing machines of RE languages. Okay, this is emptiness problem of RE languages. So similarly, if I say L of M is a 0 star 1 star, then remember, then the same thing. This is regularity problem. Correct? The same thing. This is regularity problem. This is not regularity problem. Okay. Next, this is being 0 star 1 star problem. I can say this is being 0 star 1 star problem. There is no this is not a standard. So I can say that this is being 0 star 1 star problem. You can say like this. So tell me here, this is non-monotonic. So finally I can say what? Non-trivial, non-monotonic. So I can say L01 is not RE. Why this is non-monotonic? Tell me, why the property is non-monotonic? Why the property is non-monotonic? For example, this language will satisfy 0 star 1 star. This language will satisfy, this is subset of sigma star. This language will satisfy property P. This is your property P. For this, the property P will be true. For this, the property P will be false. And both are RE languages. And both are RE languages. Is this clear? Let me know. So this is non-monotonic property. So this is actually not RE. Okay. So these are some questions we have done. I hope it is a good practice. So tell me, did you understand all the questions that we have done in this class? In this class, in this lecture, all the questions we have done, every concept that we have seen, it is like a revision. Everything that we have seen in the decidability, from the first day of decidability, everything that we have seen, it is like a revision of that. Okay, everything. Okay, I told you. Everything, every single point, everything I told you. Okay, so this is your some questions on decidability. We will do more questions in the future lectures. Okay, we will do the complete analysis of every question. Remember, solving gate questions is not enough. Getting the answer is not enough. Getting answer somehow, that is not enough. Yes or no? This is what I say. From first day of Go classes, I've been telling you that getting answers somehow is not enough. You have to understand every aspect of the question. You have to understand every word, every aspect, every variation. You have to do the complete analysis of the questions. Yes or no? For every question, you should do complete analysis. You should understand everything. Okay. From tip to toe, everything you must understand. You are a Go classes student and it is your responsibility to understand. You should not by heart. Okay. You should not rote learn. So you should understand. So this is like a revision of everything that we have seen in decidability, but we will see more. All the gate questions we will see. So in the future also this type of sessions we will keep get I can say keep keeping. Okay, so we will keep creating this type of sessions. Okay, so I hope you understood something. I hope you enjoyed it. Okay, so now actually now we will start reduction. Reduction is not required for the gate exam. In the gate exam they will not ask you any question based on reduction. Okay, also in the gate, for the gate exam we will never apply reduction also to solve the questions, but the idea I will give you, I will solve 5 or 6 questions. I will solve on reduction only, that is enough. Okay, different variety of questions I will solve. First I will teach you what is reduction, the concept, then we will solve 6 questions, total 6 questions we will solve on reductions. Okay, that is enough to give you the idea of reduction, like what is reduction. That is enough to give you the idea of reduction, and that is not needed for the gate exam. Okay, whatever is needed for the gate exam I will tell you. And also what I'm saying, so yeah. Okay, so the next lecture will be in the evening, because I have to create the slides for reduction. I was traveling the whole night actually. Okay, the whole night I was traveling, and so I could not create the slides of reduction. So that is the reason I have taken these gate questions I've taken. Okay, all these gate questions I've taken. Now what I will do, I will create the slides of reduction, and we will have a session in the evening. Okay, in the evening we will create a session. So at what time should we start? There is operating system class also. At what time should we start? Thank you, Arnab. Arnab is saying journey of decidability looks so easy. Tell me, are you finding decidability chapter interesting and easy? Like, it is very easy concept. This decidability, undecidability, this is very easy concept. This is very interesting concept. Okay, if you, I told you one thing. Do you remember? I told you that if you solve 50 questions on finite automata, you will start getting bored. If you solve 50 questions on finite automata, you will start getting bored. You will think, oh, it is so boring. But if you solve 100 questions, 1,000 questions on decidability, you will still not get bored. You will still enjoy it. This is interesting. So this decidability, undecidability, these things are interesting. Okay, and I hope you are enjoying these concepts. You are learning these concepts, and you are solving these questions with proof and intuition. With proof and intuition, without by hearting the tables and all these things. Okay, so thank you everyone. So in the evening at 4 p.m. we will start the next session, that is reduction. Okay, okay, thank you. Arnab, for time complexity you can discuss with Sachin sir. Okay, so we will start at 4 p.m. from 4 to 6. Okay, because there is evening class for operating system at 7:30. So from 4 to 6 we will study the reduction chapter. Okay, thank you. And tomorrow we will start dbms. Okay, tomorrow morning dbms we will start. So all the TOC sessions, all the theory of computation sessions we will do in the evening, and in the morning we will study dbms. Okay. Okay, thank you everyone.